Okay, so angular motion. All right, so at the very beginning here, we started, kind of working through the kinematics equations, right? One of the first things that we learned about was linear position, right? And your position was where you were at on a number line, okay? And then if you had an object that moved, from one position to another, maybe it started here to position of 1, and maybe it walked over to here to a position of 5, then you could find your change in position, right? You just do 5 minus 1 and you get 4 meters, right? Okay? So, what we're going to be talking about this chapter is instead of talking about linear motion, we're going to be talking about angular or rotational motion. Okay? So now, instead of having our number line be a linear number line, we're going to be measuring angular position. Okay? So what you're going to do is just like you do in math class, you use polar coordinates. The end of your x-axis is an angle of 0, and then we go counterclockwise around the circle, right? Measuring your angle. Cool? All right. So, if I turn the wheel from here to here, then we can talk about the angular displacement of that piece of tape, right? Okay. And so you can measure that angular displacement in 3 different units. Okay? We could call this a quarter of a rotation. We could call it 90 degrees, or we could call it pi over 2 radians. Okay. Now we will usually be using radians. Okay, and I'll explain why in a minute. But I want to be clear that you guys understand that rotations, technically speaking, rotations is a measure of angle, right? If I say that something completes 1 rotation, I'm telling you it went around 360 degrees or 2 pi radians, right? Follow? Okay. So, in the same way that we can calculate linear displacement by doing final position minus initial position, we can find our change in angular position by subtracting. These deltas shouldn't be here. Caught it and then forgot to fix it. Okay. So your change in angular position is your final angular position minus your initial angular position. Cool? So, in English, if you rotate, say, from here to here, then we could find our change in theta, right? And you could do it in any of those 3 degrees, or any of those 3 units we just talked about, right? We could say that you're going from a position of 45 degrees to 180 degrees, in which case it would be 180 minus 45, so our change in theta would be 135 degrees, right? You could do it in rotations, and that would be, what, 3/8 of a rotation, right? 3/8 of a rotation. Or you could certainly do it in radians, right? So this thing is pi over 4, right? So this would be, what, 3 pi over 4 radians? So it equals 3 pi over 4 radians. All right, cool. Questions with that? Okay. So basically, you guys, what we're going to be doing this chapter is everything, all the kinematic stuff that we learned for linear motion, we're going to be learning the angular counterparts this chapter. Okay? All the way up through, basically up through the second law. I guess we'll be doing energy too. So, yeah.
Are they all the same, like, equations just with, like, angular acceleration?
Yeah. They'll be in the notes here. Okay. So yeah, we're gonna plow through a lot here today. All right. So, are there questions? All right. Now, all right. So let's talk about radians. So, there's going to be how do I want to say this? So when I turn the wheel, so let's go back to that where I turned it a quarter of a rotation. Okay. So when I do that, the orange tape goes through an angular displacement of a quarter of a rotation, right? Or pi over 2 radians, or whatever. But also, the tape moves linearly, right? There's a linear displacement from here to here, right? Okay? And so, very often, there are times when you want to figure out, okay, well, this thing went through this angle, but how far did it actually travel linearly? Okay? And to do that, to relate angular and linear quantities, use equations that I call, this is a term that I use, jumpers. Okay? And what it does is it allows you to jump from a linear quantity to an angular quantity and vice versa. Okay? So, this is going to be our first jumper equation. Again, that's my name for them, and we'll see sort of why I call them that in a minute. All right? In order to use these jumper equations, you have to use radians. Okay? So here's why. Does anybody know what is 1 radian? Yeah, it's an angle, right? So how many radians are in a full circle? 2 pi, right? So like 6 or so, right? A little more than 6, right? Okay? So 1 radian is about 60 degrees. It's like 58 something or other, right? Okay, but here's the definition of 1 radian. Okay, 1 radian is defined as this. If you've got a circle with a radius of r, okay, and then you imagine standing on the perimeter of the circle and walking around it, if you walk a distance around the circle equal to the radius, then the angle that you just walked through is 1 radian.
Wait, so the arc length of r, how length r?
Yep. So if you walk an arc length equal to the radius around the perimeter of the circle, the angle that you've subtended is 1 radian. Fancy word, right? Okay, good?
How long has it taken me for years?
I don't know. Don't get me started. All right, are we good? Is everybody cool with that? All right, great. So, why do we care? Well, what does that mean? That means that if I am on a circle that has a radius of arbitrarily 10 meters, and I walk a distance of 2 radians, then I know I went 20 meters, right? That's what this equation does. Right? It tells you how far you went by taking the angle that you walked through and multiplying it by r. So this r here is really, it's a conversion factor that converts from meters to radians. Does that make sense? Okay. Now, that wouldn't work if you used degrees, right? Because 1 degree is not the same as whatever your radius is, right? It only works for radians because that's what the definition of radians is for r. Yes. I did, yes. Thank you for reminding me. Tell me the thing. Yeah, cool. Thank you for double checking. All right, does all of this make sense? And I got your email, by the way. Let's talk before we leave today. Okay, so, I don't know. I guess we should probably do a quick example of this. So, example. I don't know, a racetrack. The radius. Basically, the main reason I want to go through this example, it's a simple example, but I want to make sure you guys understand how these jumpers work, and so that you can see how the units work out. Okay? Thanks, Matt. All right, so a racetrack has a radius of, I don't know, whatever, 50 meters. Who cares? Car goes, I don't know, through an angle. It's not how you spell through. An angle of, I don't know, let's say 4 radians. Then how far did it go?
So, by the thing is pretty close.
Correct, yeah. Everybody good? All right, so let's make a quick little drawing here. It's not going to be anything fancy, but so, we've got this circular track. Okay, each radian is about 60 degrees, so we're going to go about 240 degrees or so. So the idea is we're going to go through 4 radians. So 1, 2, 3, 4 radians, right? And each one of those radians is 50 meters, right? So our change in x is our change in theta is r. We went through an angle of 4 radians times, and here's what I want you guys to understand. This r is really a conversion factor. 1 radian is the same as 50 meters on this circular track. And so that means that we went 200 meters around the track. Cool? And obviously you can go the other way, right? If I give you the distance, then you could do change in theta equals change in x over r. And that would give you the angle that you went through, right? Let me say one other thing and then I'll get your question, okay? All right, so is everybody okay with this? Look at this. We learned that in, I don't know, 5th grade. I don't know when you learned that. It's the same thing, right? This is how far you go around the circle in one rotation, because that's 2 pi radians. And each radian is r meters. Cool? Ethan? Sorry, say it again. Correct. Yeah, and so the units in this chapter get a little bit dodgy because a lot of times radians sort of magically appear and disappear, and that's why. Because often when there's an r in an equation, it's really meters per radian, but not always. So, and you'll see there are going to be a couple times when it's going to be like, where did that extra radian come from? And you know, so. All right, are we good? Sure it is. I mean, yeah, it's a measure of angle, and it's about the same as 58 degrees. So, I mean, it's a ratio. Sorry. Sure. Yeah. I mean, 1 degree is 1/360th of a circle. Sure. But yeah, I would take issue with I don't know.
It's an arbitrary set of standards that makes math like
right. Okay, are we good? Would you say physics what? All right. Everybody good? All right. All right, so the next thing we learned about at the beginning of the year was average velocity. The next thing we learned about at the beginning of the year was average velocity. We discovered that you can find the average velocity by simply taking the displacement and dividing it by the time, right? Okay? So, if I wanted to find the average velocity of this piece of tape, I would take the distance that it traveled and divide it by the time it took, right? Well, now we're interested in not how far the tape moved, but the angle that it rotated through, right? So as this is spinning, it would make sense to say, oh, that wheel is spinning through, whatever, 45 degrees per second, right? Like every second it's going 45 degrees, or whatever it is, right? Okay? So all we're doing, you guys, is now instead of measuring our speeds or our velocities in terms of meters per second or miles per hour, we're going to measure it in terms of the angle that it turns through every second. Okay? So, you know, if I spin this wheel and it goes around, you know, whatever, 2 times in 5 seconds, then, you know, you can figure out your displacement divided by the time and find your angular velocity. Cool? The big thing to note, though, is that gives you an average, right? For the same reason that this is an average. Okay? Because it's just, you're just saying, well, I went this far in this much time, but maybe you sped up or slowed down, right? Like if I, you know, let this slowly stop and we count the amount of time as it goes around until it stops, then the velocity during that time would be constant, right? Unfortunately, it's really big variance in it, so it's not going to stop. But are we good? Okay. All right. But notice, watch what happens. So this is the same as change in theta r over t, right? By the jumper equation we just learned. Oh, and this is omega average times r, right? So we get that same kind of jumper relationship we had before, right? Oops. In other words, a minute ago we learned this equation. Change in theta, nope, sorry, what if I read it the right way? A minute ago we learned this equation. Change in x equals change in theta r. Now we've got this one, b equals, sorry, this is the Greek letter omega. It stands for angular velocity. Okay, neglected to say that. All right, but so notice, these jumper equations are always the same format. It's always linear value equals angular value times radius. And the reason that works is because when you measure your angular quantity in radians, then 1 radius is equal to 1 radian. Alex? So that was the next thing I was going to talk about. Yeah. So, or degrees per second or rotations per second. But usually it's understood to be radians per second. Yep. Yes. Did you? Oh, I got you. Yeah, I'll take it. Thank you for reminding me. Okay. I think we're good up to there. Does that make sense, Alex, why that's true? Why multiplying by radius converts it over, or do you want me to say more about that?
I mean, I guess I've done like problems that weren't usually math problems
Right. Right. So here, all right. So let me see. Maybe there's an example here. I know I did an example somewhere. Let me wait until I get to this example in a minute, and I think you'll see why it works. Okay. All right. Okay. So the big thing here, you guys, that I want you guys to be getting out of this is that for every linear value we learned about when we did kinematics, there's an angular counterpart, right? So velocity measures how many meters you travel per second. Angular velocity measures, how many degrees or how many radians or how many rotations you go through per second. Cool? All right. And then one other thing I want to comment on, I talked about this jumper equation down here. This jumper equation works whether you're talking about average or instantaneous velocity. Okay. So in other words, if this is average velocity, this is average angular velocity. If this is initial velocity, this is initial angular velocity. You know what I mean? So as long as they're the correct corresponding value, it'll allow you to jump between the linear and angular values. Cool? All right, cool. So notice these angular quantities can be either positive or negative, right? Like when you rotate, you can go so that your angular position increases or so it decreases, right? Okay, and that indicates that it's a vector, okay? So I know you guys learned the right-hand rule last year, yes? Yeah. Okay, so technically speaking, with all of these angular values, to find the direction, you use what's called the right-hand rule, okay? So if you've got an object that's spinning clockwise, and I know you guys learned this thing, I honestly never learned it that way. I always just learned this. You curl your fingers in the direction of rotation. So that's the direction of the angular velocity or the displacement or whatever, okay? And we'll talk, it's going to come up again when we do torque, okay? But, so in this chapter, honestly, it's not going to be an issue because everything we're doing in this chapter is going to have a fixed axis of rotation. So there's really no reason why you can't just use counterclockwise as positive and clockwise as negative. All right, and that'll totally work for everything we're going to do. So if you rotate this way, it's positive. If you rotate that way, it's negative. Cool? All right. We'll talk more about the right-hand rule when we get to torque. For now, I'm basically just going to stick with this. And I'll be honest with you, there are very few instances when you really actually have to do the right-hand rule for torque. Okay? So, cool? All right, so, if the wheel spins this way, its angular velocity is positive. If it spins that way, it's negative. Cool? In terms of the right-hand rule, the angular velocity points that way for that vector. Cool? Cool. All right. All right. Everybody good? All right. Good. Do I want to talk about that? I guess it doesn't matter. Okay. All right. So let's do an example. Yeah.
Why wouldn't that settle with the same direction as the angular displacement?
It does, in that if your angular displacement is from here to here, then your rotation is this way, right? Yeah. So it's still, what is that, counterclockwise, right? Or are you worried about this?
Yeah.
I gotcha. Okay, so the, how do I want to say this? So the right-hand rule isn't really defining the direction of rotation. It's defining the direction of the axis of rotation. Okay? So when we say the angular velocity is that way, I'm telling you that the axis about which the object is rotating points that way.
Yeah.
Yeah.
Oh, I gotcha. So it's the axis about how would you say it? It's the axis about which it's rotating such that it's rotating counterclockwise.
Oh,
Right? Because look, so right now, you guys, here, for you guys, is it spinning clockwise or counterclockwise? For me, it's spinning clockwise. Look.
Whoa.
Right? Okay? But use the right-hand rule and tell me which way it's rotating. I can't do it. No, why am I dumb? Right? Everybody's thumb is pointing the same way no matter where you're standing, right? So the right-hand rule gives you a unified way where no matter where you're standing, everybody's going to agree on which way it points. So that we can agree what way it's rotating. Right? So, from my perspective, it's spinning clockwise. Sorry? Angular velocity vector, but yeah.
Does it come in anywhere the man's lines?
It will when we get to angular momentum. So like when we get to this thing, you guys I think probably saw at some point, right? So when we get to that, it'll be an issue. But are we good or no?
Yeah.
Okay. Yeah. Honestly, it's going to be, if it's an issue, it'll be very, very minimal. You really, 99% of the time when you're doing mechanics, you can get away with just clockwise, counterclockwise. There are very few examples where the right-hand rule is that important in mechanics. When you get to E9, it's much more important. But cool? Okay. So let's go through this example and see if we can kind of figure out what's going on. And I want to make sure that I focus on Alex's question about how that jumper equation works when you're talking about angular velocity as opposed to displacement. All right, so here we go. So we got a DVD spinning around in the player, spins at 1600 RPMs. So, oops. So 1600, instead of writing RPMs, I'm going to write that as rotations per minute. All right. Now, historically, we probably would call that frequency, right? And that would be appropriate. That would be fine. Wouldn't be wrong. But because we're talking about angular motion, I want to encourage you to think of this as angular velocity. Right? Because what I'm doing is I'm telling you the angle through which it turned, 1600 rotations, right? That's some number of degrees per unit time, right? So this is technically speaking an angular velocity. So I'm telling you the angle it went through per unit time. Yeah. So you could stop right there. Right? Now, usually in the textbook, when they ask you for angular velocity, they want it in radians per second.
Will it tell you that?
Or
does it just expect it?
I think it just expects you to, but then they're not totally consistent with it. You know what I mean? Like there's sometimes when they arbitrarily just do it in revolutions per second. So honestly, you guys, I'm not going to get too worked up about it. Here's what you need to know, though. The only time you absolutely 100% must use radians is if you're using one of those jumper equations. Other than that, you're done right here if you want. Like if this was a test question, you put that, badass. Cool? Because that's right. That is the angular velocity. All right? But because it's most often measured in radians per second, I want to show you how you convert it. So it's just, it's dimensional analysis, right? So one rotation, oh, that's the same as 2 pi radians, right? And, ouch, 1 minute is the same as 60 seconds. So multiply it out and you get 170 radians per second. Everybody good? All right, now, it says if there's a scratch 5 centimeters from the center of the disk, find its velocity. So check it out. The idea is our scratch is turning through 170 radians every second. If it's 5 centimeters out, how far is it going to go every second then? That's not how I want to say that. How far does it go with every radian? 5 centimeters, right? Each one of these radians is equivalent to traveling 5 centimeters, right? So that's all, literally, that's all we're doing. V is omega r. We're going 170 radians every second. And I know that on my circle, because it's got a radius of 5 centimeters, I know that 1 radian is equivalent to 5 centimeters. Right? Every time I go 1 radian, I'm going 5 centimeters. Does that make sense, Alex? Everybody? Cool. And then obviously you can convert that into meters, right? 100 centimeters, 1 meter. So a lot of this in this first chunk, you guys, is going to just be factor labeling, getting your units to be, you know, whatever units the answers are in.
Okay, so angular velocity is the same as
Divided by time. Per unit time, I should say.
Okay.
Good?
Wait, so yeah, it's good.
I shouldn't have said divided by time. I should have said per unit time, because because right.
I know.
Okay. Everybody good? Okay. So now we got to figure out how far the scratch will move. Well, that's like distance equals rate times time, right? Check it out. Displacement is velocity times time, as long as the velocity is constant, right? Here we're just talking about the magnitude of the velocity, right? So let's see, we're going 8.4 meters a second for 45 seconds. Gives you 380 meters. Cool? All right, now part D, there are 2 ways to do it, and I would like you to understand both ways. So I think there's value in understanding how to attack these problems from 2 different directions. I think this chapter, more than any chapter we've done so far, is going to be, like, for every problem, there's going to be like 10 different ways you can solve it. Okay? Because what you'll find is the equations are sort of interlocked, and so, you know, you can go this way and then down, or this way and then across, or whatever. You still end up at the same spot. All right? So, through what angle will the disk turn? So, anybody see a way to do it? Sure, the guy.
Using the angular velocity, you multiply that by the time.
Oh, great. So you're saying we know that linear displacement is linear velocity times time. So I'm hearing you say that angular displacement must be angular velocity times time, right? Rearranging that equation that Alex was asking about a second ago.
Oh, it's, yeah. Oh, okay.
Right? That's change in theta over t, just rearrange it by it. It's not a word.
So it's literally just distance equals rate times time. So.
Except we're measuring our distance in radians. Good, you guys? Okay, so let's see. Our angular velocity was 170 radians per second. And we're going to do that for 45 seconds. So multiply it out and you get 7,500 radians, which you could certainly convert into rotations. Which, incidentally, if I ask you how many rotations something goes through, I'm asking you for the change in theta, right? If I ask you how many rotations something goes through, that's change in theta, right? Because 1 rotation would be 270 degrees. So I think again, 1 rotation would be 360 degrees, right? Follow? All right, so this was one option. Solution number 1. Anybody see another way that we could also find that displacement? Sure. By the radius, yeah. Right? Remember, you guys, those jumper equations are going to be super, super valuable for you because they allow you to jump between a linear and an angular quantity or vice versa. We just found the linear displacement. So, I know that linear displacement is angular displacement times radius. That means angular displacement is linear displacement divided by radius. So for us, we went, how far did we go? 380 meters around a circle with a radius of 0.05 meters. So divide that out, and you get 7,500 meters, or radians. I guess it doesn't work exact because of my rounding, but 7,600. But if you're careful with your sig digs, it'll work out. All right, cool. That's disappointing. I'm sorry that happened. 1,700 times 45. Oh. This should have been 7,600 up here. Sorry about that. Okay, are we good? All right, questions about how those angular and linear quantities sort of relate to each other? Okay. All right, so next one. Bowling ball rolls at 18 miles an hour. The ball has a radius of 11 centimeters. Then, assuming the ball doesn't slide at all, we're going to find some stuff. All right, so we got to talk about rolling. This is going to become, next chapter, when we get to chapter 11, rolling is going to become even more important. But for now, let's just talk a little bit about some kind of basics. So check it out. Suppose I take this wheel and roll it so that the piece of tape goes around exactly one time. All right, not numerically, but conceptually, how far did the wheel just roll? One circumference, right? So when something is rolling, the linear displacement of the object is equal to the linear displacement of a point around the outside edge of the object that's rolling, right? Okay. By that same logic, that means that the linear velocity is the same as the linear velocity of the point going around the outside, right? Does that make sense, you guys? Okay. So that's useful anytime you've got something rolling. You know that your linear values at which the object is moving correspond to the linear velocities of a point on the outside edge of the object. So for us, when I tell you the bowling ball rolls at 18 miles an hour, that's the velocity, right? I know that the radius is 0.11 meters, and we're trying to find the angular velocity. So this one's just kind of factor labeled, right? So I guess we should convert that to meters per second, shouldn't we? So this is good. I think this is going to happen a lot this chapter, you guys, so we might as well jot this down. You guys should know that 1 mile is the same as 1,609 meters. It's going to come up a lot. And 1 hour, you all know, is 3,600 seconds. So what do we get? 18 times 1609 divided by 3,600, 8.045 meters a second. So now finding your angular velocity is just a matter of using a jumper, right? V equals omega r means that omega is V over r. So 8.045 meters a second divided by our radius of 0.11. And again, technically, this is meters per radian, right? When I divide by that radius. And so it does give you radians per second, specifically about 73.1 radians per second. Cool. All right. How many times will the ball roll? Let's talk about this a second ago. What are we looking for? Change in. We know the change in x, 60 feet. We're looking for change in theta, right? So how many times will the ball roll? There's a couple ways of doing this. How far does it roll with one rotation? Just the circumference, right? So one option is to just convert 60 feet to meters and then divide it by 2 pi r. The other option is to find your change in theta using a jumper equation, but that would be your answer in radians, and then divide by 2 pi to convert to rotations. So I guess we might as well do it. I think that's probably as far as we're going to get today anyway. Go away. All right. So part B, let's see. So 60 feet. Oh, shoot. This one's just a bunch more factor label. Would anybody hate me if I skipped this example? It's kind of more of the same.
Yeah.
Are we good? Okay, cool. I just basically wanted to make sure we did examples where we went from linear to angular and the other way around, and I think we've done that now. Okay. So this basically just talks about instantaneous velocity and instantaneous angular velocity. Okay, so kind of in the same way that, you know, you can talk about average velocity or instantaneous velocity. You can talk about average angular velocity or instantaneous angular velocity. You know, and everything still, you know, pertains the way that it would have before. So, you know, v is velocity at an instant. Omega is angular velocity at an instant. Now, obviously, how fast something is spinning can change, right? I can have something spinning very quickly, and then it can accelerate, right? How quickly it's spinning. Which brings us to... Oh, shoot, no, I got ahead of myself, sorry. Okay, so I balked a minute ago because I told Alex that velocity was displacement divided by time, and I said that I shouldn't have said that. Displacement divided by time gives you average, right?
Yep.
Okay, to find an instantaneous value, you guys know this, you take a derivative, right? All right, those same derivative rules apply. So linear velocity is the derivative of linear position with respect to time. Instantaneous angular velocity is the derivative of angular position with respect to time. Right? It's how much your angular position changes per unit time. It's the exact same thing. We're just using radians instead of meters, or degrees instead of feet, or whatever. Cool? So, you know, and then the differentiating rules are, you know, the exact same thing we've been doing. Just you'll be, you know, differentiating angular position instead of linear. Okay. And then you've got that jumper equation. We already talked about the jumper equation. I think that's all fairly straightforward. I don't think we have time to get through acceleration, so let's stop there. We'll pick up here tomorrow. Okay. I'm going to stop there.